Welcome. This is going to be the last section for Chapter 1, 1.6, and we're going to be talking about exponential functions. Feel free right now to go ahead and maybe pause this to go ahead and make sure you record this on your notebook. The next available page, we have the essential question: can identify and graph exponential functions. Exponential function, what's the definition? Well, it's a nonlinear function that has a certain shape, and we're going to talk about that shape here. But we have some characteristics, and so we have this table to go ahead and show us. What I would do is maybe also kind of box this so it gets used to this right here, the general equation for an exponential function. We have this trend in our data set. So we have for every x value, so notice our x values, we're going up by a constant rate. So we're going up by 1. So we go from 0, 1, 2, 3, and 4. So we're going up by 1. Okay. In terms of my dependent variable, my y variables, what's happening there? Okay, we're multiplying by 2. So we're not going up by a constant rate. We're going up by a constant factor. So we're multiplying by a factor of 2. So the difference between the constant rate and a constant factor is over here we're adding 1. Over here we're multiplying by a certain factor. In this case it's 2. So if we have characteristic, and you want to talk about characteristics, maybe draw this on the side, is that we have the general shape for exponential functions. Looks like the letter J, like this. It goes up. So it's going to be called exponential growth. We also have exponential decay, and I'm going to put it over. I guess I call this growth. And over here we can call this. The other example is when you have the opposite of growth, you have decay. So I like to think of the letter J, the capital letter J, because we have kind of a J shape for growth and decay. And again, this is decay. How do you know something's is decaying or growing? The general rule is from left to right. From left to right, if we're going down, we call that decay. From left to right, if we're going up, we call that growth. Okay? Again, feel free to go ahead and pause whenever you can. So we're going to talk about growth. If you can't see this, I'm going to try to interpret it over here. This is going to be some characteristics of what a growth function looks like in terms of an exponential function. It depends on the b value. Okay, b has to be greater than 1. If b is greater than 1, then we have growth. And again, we can have values that are greater than 1. We have 2, 3, 4. So those are values that are greater than 1. And when we graph this, that b value is going to be my y-intercept. So if my function, let's go ahead and graph a real one. If my function has a b value of, let's say, 2 to the x, that 2 is my y-intercept. So I know it's going to cross at 1, 2. And that's going to be a value of 0, 2. Which means at this point, my exponential function is going to come like this. And it's going to cross there. It's going to go up. Okay? That's what that means. Okay? So in terms of my b value, how does it affect the function? Well, again, it tells you that it crosses there. Okay, let's do another one. Let's say y equals 4 to the x. Again, what's my b value? My b value in this case is 4, so it's going to cross at 0 and 4. It's going to go like that. Okay? So we have that information there where the b value tells us where it crosses, but also if it's going to be a growth or decay factor. Another thing I want to throw in here is asymptote. What does the word asymptote means? It means, in terms of an exponential function, it means it's a value that the line approaches but never touches and never crosses. In this term, I'm saying the asymptote is the y value of 0 It approaches the y value of 0, but it never touches the y value of 0, it never crosses the y value of 0, it approaches it for infinity. Or you could say the line approaches the x-axis, but never touches the x-axis or never crosses the x-axis. So that's what an asymptote is. In this case, it's going to be a horizontal asymptote. It's a value that the line approaches but never crosses for infinity. So no matter what, you cannot you cannot cross that value. In this case, my asymptote here is the y value of 0, or you can say my x-axis. That's my horizontal asymptote for over here. Okay. So again, this is growth. Now let's go over decay. So notice decay from left to right, we're going down. Similar characteristics. Kind of just the opposite because we're going down. So in this case, we have the same appearance, y equals b to the x. This time it tells us that it's going to be decay. How do we know it's decay? Again, it depends on the b value. So in this case, b has to be greater than 0, but less than 1. If I have a scenario like this, then we have decay. And so we can talk about what are some b values that are greater than 0 and less than 1. Well, how about 1/2? About, let's say 1/4, 1/5, 3/4. So again, those are all values that are going to be fit in this category here. So if we want to do that, let's go and see how it looks like. Let's do 1/2. 1/2 raised to the x. Okay. Well, same thing as before. My b value is going to be where? It's going to be my y-intercept. So if 1/2, let's say this is going to be 1, this is going to be 2, this is going to be 1/2 right here, or 0.5. Okay, 0.5. So at this point, at 1/2 or 0.5, that's going to be where my function is going to cross. Okay, there it is. So if we have that there, we have the y-intercept at 0.5. So what is this point? This point would be 0 and then 1/2. And again, from left to right, we're going down. This also, again, we have a horizontal asymptote of the x-axis, meaning that this line is going to approach the x-axis. It's not going to touch it. It's not going to cross it. But it is going to approach it for infinity. And so here it says that the range is going to be, oh, I guess I did forget to mention the range, domain range for the first one. So for the domain range, again, for the previous one, because we're going to go forever to the left and forever to the right, we're going to say that the domain is going to be all real numbers for exponential functions. And then the range, again, how tall it is, well, we're going to say that it's going to be, so again, range, domain, we're going to say all real numbers for both exponential decay and growth, because the graph goes from ever to the left and to the right for infinity. In terms of range, again, how tall the graph is, how high it is, well, it doesn't go below 0, it doesn't touch 0, so this means that y has to be greater than 0. Okay? So again, an example of growth and decay depends on my b value. Okay, evaluating exponential functions. We're going to do here is going to create a maybe get a t-chart maybe. Sure, let's create a t-chart. So we have x values, then we have the y values, And then again, these are my inputs. So as my inputs get substituted for my x value, what's my output? So let's go ahead and do that. So we have y equals 2 and to the negative 1. That's going to give us 2 over 3. So as negative 1, again, it's going to give us 2 over 3. Why 2 over 3? I guess I went fast there, but you can't have negative exponents. So what you do is you bring the 2 and 3 to the 1. 3 to the 1 is just 1, so we get, okay? So then we're going to do another one. We're going to do, I'm going to erase this so I can do it. We'll do 0, so y equals 2, 3 to the 0. Anything to the 0 power is just 1. So 1 times 2 is just 2. So we can say that my x value is going to be 2. So then we say, well, what's happening here? Well, the next one, for x value of 1. So again, exponents first. 3 to the first power is 3. 3 times 2 is 6. So for my input 1, my output is 6. Let's go and do another one. Let's do y 2 to the 3, and then we're going to raise it this time to the second power. Okay, exponents first. 3 squared is 9. 9 times 2 is 18. So we say that for my input being 2, my output is 18. Okay, so if we look at this trend now, this trend fits the characteristic of an exponential function. Why? Because my x values are going up at a constant rate, plus 1, plus 1, plus 1. My y values are going up by a common factor. What's that factor? Well, it's going up by a factor of 3. Multiplies by 3, multiplies by 3. So again, what's happening here is we're going up by a factor of 3. We're multiplying by 3 every single time. Multiplying by 3, multiplying by 3, multiplying by 3. And so again, this fits the characteristic of an exponential function. So if you can't see the function based off the data, you should be able to say, hey, is this a growth? I'm sorry, is this an exponential function or not? And again, if it fits those two characteristics, then you're going to say, hey, that's an exponential function. So graphing exponential functions, kind of the same thing they did before, but now we're going to incorporate a graph. Range, we know that the range is going to be how tall it is. The domain is going to be all real numbers, and we'll see about that. And we'll come back to the range in a little bit. So what we're going to do is, again, we're going to make a table, and we're going to put in our x values. We're going to do it on our heads. I'm going to do it on my heads, and then we're going to go from there. So we have 2 raised to the negative 4th. Well, shoot, you can't have that. So you know what? I'm going to go ahead and do it here. So we have y equals 4 to the negative 4. That turns into 4, 2 to the 4th. So what does that turn into? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we have 4 over 16. What does that turn into? That turns into 1 over 4. So 1/4. Boom. 1/4. Let's do the other one. Y equals, again, 4 times 2. We have negative 3. Same thing. We can't have negative exponents. Negative exponent property. So we have 2 to the 3rd power. So we have 2 times 2 is 4, times 2 is 8. So now we have 4 over 8. What's 4 over 8? Well, that's just going to be 1/2. We're going to do it again. 2 raised to the negative second power. Once again, you can't have negative exponents. So we have 4, stays on the top. We have 2 squared. 2 squared is 4. 4 over 4 is just 1. So you can already see what's happening here. We're multiplying by a certain factor. Okay? We're multiplying by 2, it seems. So 4, again, we're going to go and say that we're going to raise the 2 to the negative 1. So what does that look like? Well, again, you can't have negative exponents. So we bring it down to the bottom. 2 raised to the first power. 2 raised to the first power is just 2. 4 divided by 2 is 2. So you can keep going, and we can keep proving this, but we can see now that we're multiplying by 2. Multiplying by 2. We'll do one more, and then we're just going to finish it off. 4, 2 raised to the 0 power. Anything raised to the 0 power is just 1. So 1 times 4 is just 4. So indeed, we are multiplying by a factor of 2. So what's 4 times 2? That's 8. What's 8 times 2? That's 16. Okay? So what we're going to do now is we're going to graph that. We're going to graph that, and we'll see what kind of shape it has. Now, based off that, I can tell you right now that it's going to be growth. It's going to be growth. And let's see. So, negative 4, negative 1, negative 2, negative 3, negative 4, x value negative 4, and then 1/4. 1/4 is just 0.25. Okay, so if this is going to be a y value of 1, y value of 2, y value of 3, y value of 4, 5, 6, 7, and so on and so forth. Let's do 8. 8. Okay, if we're here, right, this 1/4 is 0.25, so we're going to be close to right there. I'm going to make a dot right there as best as I can. Okay, first dot. Next, we're going to have negative 3. Negative 3 and 1/2. So 1/2 is going to be right about there. Now we're going to have negative 2. Negative 2, we're going to have a value of 1. Negative 1, we're going to have a value of 2. There we are. Value of 0 for my x value, we're going to have a value of 4. There we go. Value of, let's say, 1. We're going to have a value of 8. So we're going to be way up here. And then a value of 2, we're going to be double this. We're going to be way up here. So like 9, 10, 11, 12, 13, 14, 15. We're going to be way up here, right out of space. Okay. But if you were to go to connect these dots now, you would see this has a J shape. A capital J. A capital J, and it just goes up like that. So that's how we graph. I'm sorry, it's not very visible, is it? But that's how we graph exponential functions, by making a t-chart and then plugging in our values. Before we finish, domain. So again, domain, we said it was all real numbers. My range, so y is going to be greater than, so again, this is not going to go below the y-axis, I'm sorry, the x-axis. So y has to be greater than 0. And there we go. We have some real world problems here that we're going to go over. This is a lot. So if you want to go ahead and pause this right now. You can pause this and then read it, but I'm going to explain it. So we're modeling real life quantities, and so we're going to learn how to use exponential growth models or exponential decay models, and which one correspond to certain scenarios. So in here we're going to go over all the components to these equations. We have, so y determines how much growth we have in investment, and y can also tell us how much decay we had in an investment, like in a house, a car. Depends on what kind of car you buy. The value can go up, the value can go down. If you buy a house, the value can go up, can go down. And so we're going to talk about how we can calculate that using real data and using these equations. So A is going to be the initial amount that you invested in, that you had. So if you bought a house for, 200K, 400K here in Leavenworth, now it's probably worth like $1 million because the housing market is ridiculous. So that's going to be growth. If you had decay, maybe you bought a brand new car 3 years ago, guess what? It's not worth the same because now it went down. So again, let's say you bought a car for 30K, 40K, that car is no longer worth 30K or 40K after a year later or 2 years later. So those are some examples. So again, A is going to be the initial amount you had. R is going to be the rate at which something is gaining value or losing value. So percent lost, percent gained. And then T is going to be the time factor. So time, in terms of years, months, seconds, so on and so forth. So we're going to go ahead and use this model. Notice that this is growth when we have plus. That's decay when we have minus. Okay? So let's go ahead and use this content, and let's go to the next one. We have an example here. We have growth or decay. Let's look at the scenario. You deposit $500 in a savings account that earns 7% interest compounded annually. So that means it earns 7%. So if it earns 7%, that means we have good stuff going. We have positive stuff. So we're going to use the positive one because we're not losing, we're earning. When you earn, you're growing. So we're going to use that one. So we're going to say, well, it's that one over there. So we're going to say it's going to be y equals A and then 1 plus R. And then all we do is we plug in our information. What's the initial amount I had? Well, the initial amount I had is $500. 1 plus, the trick here is we're not going to put 7%. We're not going to put 7. We're going to put the decimal amount. So how do you convert percent to decimal? All right, you just move the decimal over twice to the hundredths place. So it becomes 0.07. So again, if you want to review how to convert percent to decimal, maybe look at a different video. But all we're doing is we're moving the decimal over to the right 2 times, and we get 0.07. And then we look at the questions here. Write a function that represents the balance after t years. Boom. This is A. That's the answer to A. So this represents a function that depicts that scenario after t years. Okay, this models this. Now, if we want to know after 2 years, then we actually plug in the value for 2. So again, we're going to do number 2. So this is number 1. Number 2 is y equals, again, same scenario, but now they're giving us specifics. Now they're giving us specifics. Now they're giving us years. So 2 up there. Put this in your calculator. You can use Desmos. It's a free calculator, graphing calculator. And when you calculate this in your calculator, you should get, again, parentheses first, exponent, and then you multiply. Don't multiply. Again, just follow the order of operations. If you do that, you should get $572.45. Okay, so that's how much you've made after 2 years if you don't touch your money. So after 2 years, if you have $500 invested, that's how much money you gain. So it really is how much you put in there. So the more you put in, the more you're gonna get out with in terms of this interest rate. We have a different scenario here. You buy a used car for $6,599. Its value decreased by 12% every year. So again, decreased, magic word there. So it's going to be decay. So we're going to use this one. So write a function that represents the value y in dollars of the car after 2 years. So again, y represents money. How much money have you lost in this investment? So the initial amount is $6,599, and then 1 minus, what's my interest for you? My interest is 12%. Decimal, that's 0.12. And then t, okay? So this is a model. This tells us how much we'll lose if we know how many years. Again, this is just the model. We're not told to say how many years. We're not asked for that until question, I guess, part 2 over here. What is the value of the car after 2.5 years? Well, let's find out. This is part, let's label this. This is part 1, part 2, part 3, part 4. So again, this is part 1, this is part 2. Part 2 is kind of the same thing. We're going to plug in the same values. And then we have to talk about 2.5 years. That's 2.5 years. You put that in your calculator, and that's going to give you 4,793.85. So now you have lost a little bit of change here in that car, so maybe not a good investment for a Pinto. What is the value after 20 years? Let's see how much this bad boy is worth after 20 years. So again, 20. Put this in your calculator. PEMDAS, order of operations. This car is now worth a whopping $511 with 85 cents. So that's not a very good investment after 20 years. And then number 4. Number 4, according to the model, when will the value of the car be 0? Never. The reason for that is because if we go ahead and graph this is a decay model, so this is a decay, right? We know that the function can never approach what value? It can never approach the y value of 0. So therefore, according to the model, when will the value of the car be 0? Never, because there is a asymptote here, meaning that this function can approach 0, but will never reach 0. That was it for today. This was a long video. I apologize for that, but it's important and it's going to help you out in the next class.